Hi, this is Calculus 12, Chapter 4.3. We're going to do a complete example of a curve sketching exercise. Just a reminder of the steps. The domain, determine the domain for f of x. Intercept, evaluate f of 0 for the y-intercept, and set f of x equal to 0 to look for the x-intercepts. And checking for asymptotes, you want to see if the limit is finite at infinity and negative infinity for horizontal asymptotes. We want to check for NPVs in the denominator to check for vertical asymptotes. So we have a right limit that equals infinity, or a left limit that equals infinity, a right limit that equals negative infinity, and a left limit that equals negative infinity. We can also check for slant asymptotes, where the limit as x goes to infinity of f of x minus mx plus b in brackets equals 0. And for rational functions, this occurs when the degree of the numerator is 1 more than the degree of the denominator, such as x cubed over x squared plus 1 in brackets. We want to find the intervals of increase and decrease, so where the slope is positive and the slope is negative. We want to find the local minimums and maximums. We do this by finding the critical numbers first. That's where the derivative equals 0 or does not exist. And we can use the first derivative test to check this change of sign. And we can use the second derivative test to check for concavity. We also need to calculate the concavity and inflection points.
Remember.
I said this before, but here it is written down. Use the second derivative test only if the second derivative is easy to calculate. So if you're using the quotient rule for the first derivative, then it's probably not a good idea to do the second derivative test. Okay, the example is s of t equals 3t squared minus 2t cubed. This is a polynomial. And polynomials have a domain of all reals. This is a cubic or an odd degree polynomial, so the range is all reals. Let's find the intercepts, x-intercepts. 3t squared minus 2t cubed equals 0. We factor, we get t squared, 3 minus 2t equals 0. So our roots are 0 and 3 over 2. Our y-intercept is just s of 0, and that equals 0. Asymptotes, there's none because it's a polynomial. Okay, let's find our derivatives. S prime of t equals 3 times 2t minus 2 times 3t squared. So that's 6t minus 6t squared. S double prime, the second derivative, equals 6 minus 6 times 2t. That's 6 minus 12t. Okay, now we find our critical points. We have 6t minus 6t squared equals 0. We factor out a 6t and we get 1 minus t equals 0. T equals 0 and 1. We find our inflection points. 6 minus 12t equals 0. Negative 12t equals negative 6. T equals 1/2. Okay, we'll do our first derivative test. So we need points between our critical points. So we have -1, we have a half, we need to be between here, and we'll pick 2. So S prime of -1 equals 6 times -1 minus 6, that's minus 12, that's less than 0. S prime of 1/2 equals 6 times a half minus 6 times a quarter. That gives us 3/2. That's greater than 0. S prime of 2 equals 6 times 2 minus 6 times 4. That's -12. And that's less than 0. So we're decreasing, increasing. This is a min. And we have increasing and decreasing, so we have a max there. We can do the second derivative test. S double prime, and we have to do it at the critical point, so 0. So 6 minus 0, that's 6. That's greater than 0. This is concave up. S double prime of 1 equals 6 minus 12. That's -6. This is less than 0. This is concave down. So concave up tells us we have a min. Concave down tells us we have a max. Okay, we need to actually calculate our values. So S of 0 equals 0. S of 1 equals 3 minus 2, and that's 1. We need to calculate our inflection point, so S of 1/2 equals 3 times a quarter minus 2 times an eighth. That's a quarter. It's 3/4, so it's a half. Okay, you should always double check your checklist. We've done the domain, we've done the intercepts, we've done the intervals of increase and decrease, we've done the concavity, we've done the inflection point, we've done the critical points, and we've calculated the minimums and maximums using the first derivative and the second derivative. The choice between first and second derivative is not very different. There's only one extra calculation for first derivative, so there's no preference of which one to do. And now we just need to graph. Okay, we'll start with our critical points, 0, 0, and we have 1, 1. I'm going to change the scale here. This is 1, 2, 3, -1, -2, -3. So we want to use a scale that's going to show the features. If we make it 1, 1, then everything's going to be very tight, and it's going to be hard to see the detail. So we have 0, 0. This is a local min. It's also our x-intercept and our y-intercept. This is 1, 1. This is our local max. Because it's an odd degree polynomial, we only have local extrema. We don't have absolute extrema. And then we have 3/2, 0. That's an intercept. X-intercept. And we have our inflection point. This is 1/2 and 1/2. It's better to use fractions than it is to use decimals because fractions implies exact values. And we can draw our curve now. Try to draw it as smoothly as possible. It is a polynomial, so it's going to be smooth. And because it's all reals, you should put arrows at the end of your curves. Okay, let's mark off our intervals of increase and decrease. So we have a dotted line here, dotted line here. So we have decrease, increase, decrease. Okay, let's do a different color. Green here. We have concave up and we have concave down, and that goes to infinity. So double check that you have everything. We have our domain, we have our intercepts, our x-intercepts, our y-intercepts. We have our intervals of increase, decrease. We have our local minimums and maximums. We have our concavity and our point of inflection. And we've sketched a curve. And that completes this example.